Hello guys, Ramadan Kareem. Today we're gonna speak about the band structure lab. So from this link, which is connected directly to NanoHub, you can easily go to this website which called the Nano Structure Lab. From the Nano Structure Lab, after you sign in with your account, you can see here the geometry of the material that you're gonna study. So for example, we have bulk, and we have nanowire, and also we have ultra thin two-dimension material. For you guys, you have to start with the bulk 3D material, and then you can go and start to select the material that you're gonna study. So as I told you before, we have three options in here. One is the bulk, which is honestly the material that you use usually. We can see it in your naked eye. We have nanowire, which is 1D periodic, and we have ultra thin body, which is 2D periodic. So if we keep the bulk for now, the normal case, and here we come and see that we have several materials. You can see that we have several materials, including silicon, germanium, gallium arsenide, indium arsenide, and so on and so forth. So let's start with the silicon for now. So basically we will start with silicon with bulk 3D periodic. And we can go to physics. Here in the second part, it's basically giving you the model that you're going to use for the calculation, along with the spin orbit coupling if you want to include it, the strain, other stuff we don't need to touch with that, so we will keep it as it. We don't gonna touch anything here. You go to K-space. In K-space, we will skip this part. We are not going to touch anything here. Let's go to numerical. Here it will tell you how many K point you're gonna calculate. We will keep it the same, 30 is fine. Finally, you will start simulation process by clicking on simulate down there. After a few seconds, you will see the band structure of silicon in bulk case. As you can see, there's a lot of K points. This is E and this is K. And here is the area when you can see the band gap, like close to the zero. The best thing to do is to try to zoom into this area. So you can easily do that by scrolling the mouse down there. So basically you are touching the area around the zero and leave it. After you zoom into this area, you can easily see the edge of the valence band. See here, this is below the zero. This is the edge of the valence band. So this is the highest energy level in the valence band. And from here, this is the conduction band. And you see, this is the lowest energy level in the conduction band. It's the lowest. So this gives you a very clear sign that this is indirect band gap semiconductor. This is indirect. Silicon is indirect band gap semiconductor. So the electron needs to change its energy. So it needs to have this much of energy and also change the direction, the Q, the wave vector, in order to go from the valence band to the conduction band. So we are trying to find the lowest point in the conduction band. So as you see, the line that it makes tell you that this is the lowest point in the conduction band. And the value here is 1.133. Remember this, 1.133, the lowest point in the conduction band. Let's see the highest point in the valence band. So the highest point in the valence band is minus 0.02. minus 0.02. If you take the differences between these two, so you will do this minus this, finally will give you this. You can also get the image of this graph by clicking here. You can see that you will get two options. One of them is to download as a PDF or PNG JPG file as an image. Just download it, you will find it in your computer. Or you can get it as a data. You can get as XY, so you can go and draw it in any other software like Excel, Origin, whatever you like. So let's come back now to the nanowire case. So just go to device type. From here, instead of bulk 3D, you can go to nanowire 1D periodic. And once you click that, you will see that there are many options you can find. Of course, calculation for electrons and also the type of material, you can keep it as silicon. The job type, you can keep it as calculated, the wire band structure. For the cross section, see the wire has some cross section, could be circular, it could be other things like rectangle, triangle, circular shell, but for now we will keep it circular. We can go down here, and that's the most important thing, to select the diameter. So for example, we have done before the 1.5 nanometer. So once you click it and make it 1.5 nanometer, so you can go to physics again now and start the simulation process. Get 1.51, it's fine for now, we are just testing. Again, for exploring, we need to do both bands. We need to see the conduction band and valence band. You go to K-space, again numerics, keep the 30 for the K point, and do the simulation. As you see, it appears the previous simulation, but now it's running another simulation to give you the nanowire with 1.5 nanometer. You will see the band structure will be totally changed. So the simulation time depends on the internet, and also depends on the diameter of the wire. Sometimes it takes very long if you increase the wire diameter. So this might take about a few seconds only. See, it's done for now. And you see the simulation, it's getting the band structure. So it's totally different from the case in the bulk. So you can zoom into here and try to see the band gap obtained. See? Okay, let's go there. See, the highest point now is here, and the lowest point is here. So this is direct band gap semiconductor. And if you find the point, for example, here we have the highest point is minus 0.69, and here the lowest point is about 1.97. So you add them up. Of course, here you have minus, so you do basically 1.977 minus minus, so it's going to be plus 0.69,
and you will get the band gap for the 1.5 nanometer um, silicon nanowire. You can also download the data or download the image to keep it in your computer and use it later.